How's everyone doing? Tired, I know. I could use another day off from used Monday's holiday to get caught up, so it was a Labor Day, so that's okay. Got to keep busy. So let's see. Got our canvas. Let's let's do an overview. Guess we could do this one. Let's go this. We'll see where we're at. Okay. So we are here this week, September 4th through 8th, following up Labor Day holiday, which didn't affect our class. We still have our Tuesday, Thursday. Today, I think we'll do a good job of getting through division of polynomials and zeros of polynomial functions. They kind of interrelate to each other, which will give us all day Thursday to take a look at rational functions and tie in these skills. So today we'll focus on the skill of dividing polynomials and finding and knowing how many zeros a rational function will have, and then we'll actually get into the work of rational functions on Thursday. That'll be the end of what we need to take a look at for the test. Next Tuesday we will do a review day. To prepare for the test, I did ask the coordinator, let's see, she told me the test will have somewhat about 20 questions, maybe a little bit less. A number of them will be multiple choice. So you'll have the question, you just have to choose the right answer. We do ask that you do show your work. Again, that helps with partial credit because maybe you chose the wrong one, but because of an error somewhere along the way, that's good. But still, multiple choice, you got the right answer, we'll get you there. And then there's a couple open answer type ones where we're really going to look at the work. So we want you to show that part. And I'll give you some more updates as I should have the test itself by the end of this week. Hopefully by Thursday so I can get you there, but certainly by next Tuesday I will give you all the details that you might want to know. Multiple choice, I'm giving you the answers. Only they're hidden with the 3 wrong answers for every 1 right answer, but we'll go there. Okay, so we've got this going. Remember, as we cover things, it's in the main unit, and then there's some extra additional notes. So today we're scheduled to take a look at dividing polynomials. So we're going to look at 2 methods. One is long division, and the other one is a synthetic division, which works if in certain instances, and it's a little bit faster. Okay, so again, today's this first one specifically is just about picking up some techniques for doing some manipulative type algebra. And you'll notice I didn't have any notes on this because in my other class we don't do this. But this is being the STEM one, we will talk about dividing polynomials. And then there's a couple theorems that come in here that are pretty straightforward, hopefully. So we're going to use long division. That's the main thing we'll be focusing on. We're going to also learn synthetic division, which again you could do it with long division, but synthetic division is a little bit faster. Couple things you'll need to remember about that, and then we're basically going to put them to work on some problems. So this is a little bit just the theory behind what's going on. Basically, for every function, it can be if we have a function f of x and we have some other function d of x, if they're polynomials, if the degree of d of x is less than or equal to f of x, then we can come up with other functions that if we take d of x times q of x, we might have to add something more, but we can get f of x. So we've got two polynomial functions. It's basically saying we can make them equal as long as they're as long as it fits this, that the degrees are less than or equal, right? Because we can do that. If r of x, so this is the other function, if it's equal to 0, that's what we're adding on. That's kind of like what we would think of as a remainder. Then what we're saying is that d of x and f of x, that basically d of x is a factor of f of x. Okay, so we're going to look at sometimes we've got a remainder, so then it's not a factor, not just a factor because there's this remainder. But if there is no remainder, then it's a factor. And if it's a factor, we're going to see it's going to help us in finding zeros of the function. Okay, so that's where we're going with this. And we don't have to completely understand this because, again, we're going to just kind of get into these. What am I doing here? So I kind of changed this, and I'm let me get out. Keep. Oh, okay. Now I see what's going on. Okay, got it. Okay, so if we've got a polynomial, that's where we're starting. We're going to divide it by another polynomial, so that's kind of like the f of x, dividing it by the d of x to see what might be there. What we first have to start off with is it's going to be a lot easier if we get the first function, this one here, in descending order. So we're going to move the x to the third to the front, x squared. So that's what they did here. Okay, so they just reorganized it so it's counting down. If there was a missing term, say there was no 11x, what you'd want to do is rewrite this as 2x to the third minus 3x squared plus 0x plus 7. Okay, so we'll see just so that all the terms are there for when we do our division. So 0x would be there. So, and now what we're going to do is actually just the long division. So we'll walk through this. The slides that follow this, if you want, if you wanted to look at them, they're going to kind of detail step by step. But I find it's always easier to kind of just go through and talk through this as we do it. So what we do is we're thinking, what do I multiply x by to get 2x to the third? Well, this is x to the first, so certainly I need to get the x's to match up. So if I do x squared times x to the first, that gives me x to the third, right? But it'll give me 1x to the third, and I want 2x, so I'll do 2x. Okay, so that's the first thing I'm thinking is, what do I multiply this first term to match this up? Then I go ahead and do it. 2x squared times x to the first gives me 2x to the third. But I have to multiply the whole polynomial by this, so I also have to take 2x squared times 3. So that's going to give us, what, negative 6x squared. And then if you remember doing long division, I tried to forget all about that, what, third grade, fourth grade, whenever we learned it, and again, you learn it in different places. Different parts of the world do it differently also. I had a student from Brazil who showed me how they do long division in Brazil. It's much nicer, actually, I think. But, anyway, we're built off of the American system. And just to let you know, there was actually, like in the 1800s, they had this convention in Europe of all the mathematicians around the world. They decided to do it more like the way they do it in Brazil and many other countries. The U.S. and England decided they're still going to do it the way they've always done it, which is sort of that convention said that's the wrong way to do it. So it's a harder way. Anyway, we'll do it. So then what we're going to do is we subtract this. So we change the signs because we're subtracting from this, right? So 2x to the third minus 2x, that's 0. So that's kind of canceled out, right? And then negative 3x and plus 6x now becomes plus 3x squared. Bring down the next term, and we do it all again. Okay, and again we look at the leading term. What do we need to make to get this? And so to make x into 3x squared, I need to multiply by positive 3x. Positive 3x times x gives me my 3x squared. We see that's going to cancel out nicely when I subtract, and then I have to keep going. 3x times negative 3 gives me negative 9x. Again, as I go through, I'm subtracting, so I will change the signs. So it becomes 3x squared minus 3x, that's our 0. Negative 11 plus 9x is going to give us negative 2x. Okay, bring down the 7, positive 7. And again, we do it all again. What multiplies x to get us to negative 2x? Well, that would be negative 2. Negative 2 times x gives us negative 2x. And then negative 2 times negative 3, positive 6. And then again, remember, we need to change the signs because we're subtracting. So this becomes negative 6. And we get 0 plus 1. Can we go any further? No, there are no decimals in polynomials, so we're kind of done. We didn't get 0 at the end. We got a 1, so that means there's a remainder. And so that means what's remaining is this 1 divided by this. So it's positive, so our final answer would be plus 1 divided by x minus 3. Okay, so this is what we're saying is if you took x minus 3 times this polynomial and then added the remainder, you would get the original function. Okay, so that's all that. But you see the process of doing it, it's just kind of methodical and tedious, and you got to make sure you're doing all the things. And any questions? Okay, so then this is what the textbook had for us, step by step. Shows the same thing, but again, I could have just said here it is, that's what you do, but I like to talk through it. So again, same answer we got, hopefully, right? Yeah, pretty much. There we go. So this again, I won't spend too much time, but this is for those of that you maybe want to read through this. These are the steps we did. We arranged the terms from biggest to smallest, so x to the third, x squared. If there's a missing term, we put a 0, so that we basically got all the digits of a polynomial. We take and divide the first terms, right? The first ones to make sure that those match up. That's how we get that. And then any remaining terms we have to multiply by. Multiply every term in the divisor by the first term of the quotient. So we did all of this. I just find it's a lot easier just to kind of do it than to try to read about it. I get confused when I start reading. What are we really doing here? Oh, that's what we did. Then we subtract. That's the key part. We don't add them together. We subtract. I think when we go to synthetic division, I think we're kind of adding. Yeah, we add. So it gets to be a little different. We bring down the next term, and we do it again. We just keep going, right? So that's what we did. We did that for the first term. We get the new expression, and if there's a, let's see, as the dividend, and repeat this process till the remainder can no longer be divided. So if it's 0, that's good. There is no remainder. It's 0 divided by that. If there is some other number, then we have that. Okay. So now we're going to do synthetic division. Again, this is a little confusing because I need to hit this. So they want us to divide this number by this number using synthetic division. So we're going to set up, and then I'm going to show you how synthetic division is a little different than long division. So it's just another technique, but this works especially if we have x plus or minus something. But the first thing we notice is that synthetic division is set up to work with x minus the number. So if we have x plus 2, what this is, we're just going to have to remember is whenever we have it here, it's always going to be the opposite sign, right? So If it's x plus 2, we have to really think it's going to be x minus negative 2, so we're going to use negative 2 for doing our synthetic division. If it was x minus 2, we would use positive 2 for our synthetic division. So just kind of, the way I remember is I just use the opposite sign. Okay, and because I'm using the opposite sign, what it allows us to do is in synthetic division, we actually add instead of subtract, because we're using the opposite, right? So that's kind of, it's really subtraction without, but we've convinced ourselves that's all we're doing. So we could get the same answer if we went through and did long division on it, but what we're going to see is that we're going to do it with synthetic division. So we take this same setup. All we're going to need to do for synthetic division is we take this part, so we don't even worry about the x because that's x to the first. And then notice we take the coefficients. So this x to the third has a coefficient of 1. Notice they put, there was no x squared, so they put it 0x squared, and that's what goes here. And then negative 7, so that coefficient comes here, and negative 6. So it's much more abstract because we lose all the variable parts, but we had to make sure they were all there, and again in descending order. Now let's see if I can remember how to do this. I always have to practice again. Cool part is I like the first step. Whatever's here, just bring it down. That's the easiest part. I love that part. What's the second step? Second step is to take negative 2 times 1 and put it here. Okay, so that what I did is I take negative 2 times 1, and that goes there. Now I add these two together. 0 plus negative 2 is negative 2. Again, I'm hoping I'm doing this right. I'm only about 50% sure right now, so we'll see. Hopefully it works out. Now, I've got the notes under this, but and then I take negative 2 times negative 2, gives us positive 4. I add these two together. That gives me negative 3. Negative 2 times negative 3, positive 6. Oh, this is beautiful. Negative 6 plus 6 gives us a 0, which means there is no remainder, which means it's divided evenly. But what do we have? Well, what we have to do is come back here and say, well, this was x, this is x to the third. So notice we really did divide that up. So we have when we go to put the variables back in, they're all 1 less than what they were originally. So what this one is, this is really 1x to the second. This negative 2 is negative 2x squared, and this, oh, no. So I got to learn to subtract 1, right? That's just to the 1 power. Okay, thank you. To the 1 power. So yeah, that's why I always write the 1 power. So 2 power, 1 power, and then this negative 3 is just negative 3. So what we found out is that this whole thing here will actually factor into x plus 2 times x squared minus 2x minus 3. So notice how what we're using this for is helping us for factoring. So it'll help us find zeros and those kind of things that we're going to look for. Questions on that synthetic division? So it's a technique. We're going to use it, but we have to know that technique. And notice how it's different. You get it all in order. Take the opposite sign, x, either plus or minus something, the opposite sign. Bring the first one down, and then it's just multiply and add, multiply and add, multiply and add. Question? If it asks for it. For this one, if they just ask us to do synthetic division, we'll take a look at some of the homework to see what they're asking. But this is what we end up with. That's the synthetic division, doing it. This is a translating to what's left over. And then if they asked it, what are all the factors, we can write that out. So we'll look at some of the homework as well to see, because it's each time they're asking for different things. But the main thing is that we know how to do it. So we know how to do long division. We know how to do synthetic division, because those are the two skills we're really going to need to be using throughout these next two homework assignments, and then we'll be applying them differently for different situations. And here it is. So if they just say use it to divide, we did it, we divided it. I think that's the only, so again, I could have just showed you that, but it doesn't really say what's going on, except that, we're multiplying by -2, multiplying by -2, multiplying by -2, and that goes there. And then we're adding, right? So it's a different process. We're not subtracting, we're adding. But again, we're adding because we we have it in terms of the negative. So we're always using the opposite sign here. So in effect, we are subtracting. We just do it early. Okay. And this is going to walk us painfully through this whole process of the steps. Okay, so first put it in order. Any missing things, put a 0, x squared or 0, whatever needs to be there. Remember to write the divisor as x minus something. So if it's x plus something, it's minus a minus. If it's x minus something, then we're using the positive number. So basically, to me, the easiest way to think of it, just use whatever this is, use the opposite. So I would use a positive c here. If it was x plus c, I would use a negative c. Okay. So write the leading coefficients. So get rid of the x to the third, x squared. We don't write all those. We just write the numbers that are in front. They're set up. We've got this number with the x minus something, and we bring the first one down, and then we multiply our c times each one. It goes up, and then we add, multiply, add. Okay, kind of what we did. Okay, it's harder for me to read through all this stuff than to actually do it. Add the values, writing the sum at the bottom row. Okay, repeat it until we get all the way to the end. And in the last row, if we get a 0 like we did, there's no remainder. If there was a number left, just like in the long division, we would have, say there was a 1 left, we would have written 1x plus 2, right? So that would be the remainder, if there was 1 left, right? Let me put that if remainder. But this is part of what we're going to do, is we're going to do this and see if there's a remainder. Sometimes if there's a remainder, that means that's not a factor, right? Because we multiply by this, but then we got to add something. It doesn't go in equally. So we're not interested in that. We're looking for what's the one that we get a 0 on, because then that means there's no remainder that divides in evenly. So and now we've got a method with the synthetic division to do it a lot quicker. So that's why we use this synthetic division. Okay. Here's a theorem. Again, that means that somebody went behind here and said, okay, here's another result. Here's a pattern that always works. They probably went through and proved it all. We won't spend all that time proving it, but let's see, let's come back here. The important thing is when we take a function and divide it by this x minus c, again, in that case it was x plus 2, right? Then if there is a remainder, that's the same thing as plugging in c to the function. Now you're going to say, at least I say this, why don't I just plug c into the function and get it? Because it might be more work. Okay, so we've got this method that may actually make it easier. So we could do it either way. We could just take that number, plug it in. So we'll take a look at this example. So in this example, to find f of -4, yes, we could plug in -4 for each of these x's, and our graphing calculators could go like that. But remember, math is like this old thing, and math people change slowly, takes centuries. 300 years ago, they didn't have the calculators we have, and so this technique was helpful. Okay, we're still using it. Again, we've got calculators and computers. We could just plug that in and get the answer. We're good with it. But let's see how we could use this remainder theorem. Let me just click. Okay, I don't want to go that far. So the solution. What we're looking at is, since it's x minus 4, right? That's what this means, is we're plugging in negative 4 for x. Let's think about how that would look as a factor, right? We're saying x plus 4. So in thinking of synthetic division that we just did, what we're wanting to do is take this polynomial here and divide it by x plus 4 with synthetic division, right? So let's set this up. I guess I don't have to go all that way. I guess they go like this. So in this case, this number in here, right, we're going to use, well, this number down here, we use the opposite of positive 4. We're going to use negative 4. So when we're using this, when they give us f of negative 4, that's the one we want to use. But since I just told you we use the opposite sign, I wanted you to see that's because if we think of it as a factor, it's really x plus 4. So we use the negative 4. What are we going to put over here? Well, we get the coefficients all in lined up. So we've got an x to the third, second, first, and x to the 0. So we're going to put 3 plus 4 minus 5 plus 3. We didn't need to put in any zeros, right? Because we had everything there. What's our first step? My favorite one? Just bring it down. Yeah, so this, okay. That always gets me. Why? It's like I didn't do anything, right? But it's because remember x is going in there, so anyway. And then what do? Multiply by negative 4. 3 times negative 4 is negative 12. Add them, right? So I got negative 12 plus 4, negative 8. Negative 8 times negative 4, positive 32. We're getting big. Add, and so 28. Oh, geez, they're getting huge. Negative 4 times 28. How much?
27, no?
Oh, thank you. Yeah. That's the, sometimes I'm not paying attention. You go on autopilot and you crash. Thank you. 27. 4 times 27 is like 80. 4 times 7 is 28. 108? Is that right? 4 times 7 is 28. Carry the 2. 4 times 2 is 8. 108, yeah. And then we add these, so that should give us negative 105. What we just did is this should tell us that f of negative 4 is equal to that remainder, negative 105. If we plugged in negative 4 for each of these x's and did the math, we should get negative 105. Does anyone believe it? They say it is, it should. So, well, we could go to a graphing calculator, put it in, right? They've done it here. And yeah, a little smoother than I didn't make any errors. Use synthetic division. And we get that since the remainder was negative 105, the answer, f of negative 4, is negative 105. Again, 30 years ago, this would probably be a good technique. Now, just plug it in the calculator, get it, but it's a use of these. Okay. The factor theorem. So this is kind of a similar type thing, kind of like say, if there is no remainder, then what we've got are two factors because it went in evenly. So I kind of got alluded to this already, but if when we do this we get no remainder, or so if there's no remainder, that means it's 0, and the remainder theorem just told us, well, that means that when we plug it in we will get a 0. It tells us that what we have here is a factor of f of x, and then if we do synthetic division on it, whatever's left over, that's also a factor because there is no remainder, right? So this is a way to factor. If we know one of the factors, we're able to find another factor. So, oops, oh, I should work through this. So solve the equation, this, given that -1 is a 0. Let me do it over here, and then I'll probably have to erase it. So we know -1 is a 0. So what does that mean? It means if I take f of -1, there is no remainder, it's equal to 0. So that also means x plus 1 is a factor. Okay, so remember that this is one confusing part, is the signs sort of keep changing. And the way I remember that is f of -1, that means that -1 is equal to x, which means 0 equals to x plus 1. So just be careful because signs change. Am I using the negative, or did I take the negative of the negative? So this is just, if I'm plugging it in, just say that's what x is, solve for 0, and it'll make it clear. So we know one of the factors is x plus 1. To get the other one, again, we could use long division, but because it's x plus 1, it's got a coefficient of 1, synthetic division will be a little bit quicker. So we use the synthetic division of -1. They've got it set up with all x to the third, second, first. So we've got all our coefficients here. Oops. Make sure you get your signs right. Sometimes that's why I'll put the pluses in, just so I don't lose the negatives. Again, what is the first step? Just bring it down. So we're going to have 15. -1 times 15 gives us -15. 14 plus -15 gives us -1. -1 times -1 is +2. +2 times -3, no, not times, we're adding, is -1. -1 times -1, +2. Add those, oh good, we've got no remainder. So what is this part here? It's a factor, so we know one of the factors is x plus 1. The other factor is going to be 15x to what power? Squared, 1 less than what we started with. Good. Minus 1x to the first minus 1, and there we go. So that we've got it factored. Could we factor 15x squared minus 1x minus 1? Potentially. Potentially. It might factor. If not, do we have a method for solving x squareds? Quadratics. Yes, quadratic formula. I think this one might need the quadratic formula, so I'm going to let them do that. But see, yes.
I think the plus 2 is supposed to be plus, or plus 1, because 1 times -1 is
Okay. Negative is +2. That's -1. Which one?
You remove the sign and
times -1 equals +1 instead of plus 2.
Okay.
It's multiplying and not adding. Right? Where it says -3 plus 2, it should be -3 plus 1.
Oh, thank you. Thank you. See, I couldn't even see my own error. I said, wait, no. Okay, thank you. Okay, so it might not be as, okay. So -1 times -1. 1 times 1 is still 1. Okay, gotcha. That's the one that always gets me. Okay. Gotcha. It's good somebody's awake, right? Okay, -1 times negative is +1. Oh, but see, this is what I like about math. 2 wrongs oftentimes do make a right. I made the error twice, and I still ended up all right, didn't I? Because then I took this -1 times 1, and I got +2. Occasionally it does.
Now -3 plus 1
2, right. And then it all makes sense. So we ended up with the same answer, but I got there sort of in the wrong way. So this is now -2. -1 times -2 is +2, and so there is no remainder. So it's all good. But I don't know. I always loved it. 2 wrongs do make a right in math, oftentimes. Sometimes it's not that you made a mistake, you just need to make mistakes in pairs, and then you're usually okay. Okay, thank you. Thank you for catching that. Because remember, I post these go out on the internet, and then it makes, wait, that's like, I know that 1 times 1 is 1? No, I don't. Okay, good. So where were we? Okay, so that's it. And let's see. We'll fill in this stuff. Let's get this out of here. I think we can. So we're given that -1 is a 0. We can take that. That means that this is kind of what I wrote. The factor theorem says x plus 1 is a factor. So we can go do our synthetic division, which we've already done. I guess I was supposed to do it here. I had it set up, but lots of room. They went ahead and did it. Okay, they came up with the same thing we did, and then they rewrote it in these terms, same thing we did, right? And now, oh wait, they had a -2. That's, so I erased it. That's where I would have been off, is I was off here. It's not -1, it's -2. Okay, so I was, 2 wrongs don't always make a complete right, but we've got this part. And now I think this might factor. Let's try this. So 15 is 3 times 5, so I'm going to go with 3x, 5x. 1 times...
Not that. I just think that 15 to the is 30, so you can split it into 5x and plus 5x minus 6x.
Right. And so then there's a 2, and that's a 1 and a 2, so I'll put the 2 with the 3, so that'll give me a 6. The 1 with the 5 will give me a 5. I always do a sort of guess and check. I know there's a sort of a methodical way to do it, but I just kind of go through, and since it's negative, we want the bigger number to be negative plus, so it does factor into this. I think this thing, and then we've also got this x plus 1 here. So notice how we were able to actually factor this whole thing, but we had to have some knowledge of that there was a 0. Okay, we're going to actually, the second lesson we'll do today gives us some tools that will tell us how to find that one. So we go here. So again, we factored this into 3x plus 1, 5x minus 2, and then we knew that this part has to be part of it. And if we FOIL this out or multiply it out, we'll get back to what we started with, which is good, is what they did here. Then what they did is to find the zeros, right? Find where this equals 0. Since we have it factored, we know that x plus 1 equals 0, 3x plus 1 could equal 0, because the only way you get 0 with multiplication is if one of the numbers is 0. So we go through and we plug each of these equal to 0, and then solve. So subtract 1. This one subtract 1 and divide by 3. X equals -1/3. This one add 2. And then divide by 5, so we get x equals 2/5. So those are the 3 zeros of this function. So that's the 3 places that would cross the x-axis. And even they made a mistake. They put 5 over 5. There should be a 2 over 5. Right? They got it right here, but a copy error. It happens. Okay. How are we doing so far? So those are all the techniques. What we're going to... Good, good. That's the last slide for this part of the lesson. The next lesson we're going to get into, there's some theorems on how we can find possible zeros. Okay, and we're going to use these same techniques, so it will go very well hand in hand with what we're doing. We started. Wow, we've already got 40 minutes into this, so I think 20 more minutes will be good. I'm going to discard those. I'm going to just keep the same recording going. I think on one of them, the second part, I start the link I put so it starts about where it's at. Has anyone taken a look at that? Did that work out okay? Because when I copy the link, I have it start about where it should. If not, let me know. Okay. So now, I'm going to look at, so we did dividing polynomials. We're going to look at zeros of polynomial functions. And we pick up a couple more theorems that are kind of cool. Again, we got to remember that people were working on these sometimes several lifetimes. Several hundred years could pass to figure out these types of things, to see these patterns. So, and we expect you to get it in like 15 minutes. So it's, it's a lot of stuff that's going on. But sometimes it takes a long time to find something, but once you know it, it's like, okay, we just use it, and that's how we keep going. So we're going to use what's called the rational zero theorem. Let's back up here. So that's one thing we're going to be doing to find possible zeros. And then we're actually going to find zeros, so then we're going to go back and use either synthetic division or long division, depending upon which one we can, and then solving those equations. We're going to pick up another thing called the linear factorization theorem, and that just basically says that any polynomial can be written as linear factorizations. And then there's this Descartes' rule of signs, which, again, we won't get into the details of how it works, but we'll know that that it does work, and it's kind of a cool thing to just tell us how many zeros are, how many positive zeros there's possibly, and how many negative zeros there are, and whether there's any of those. So a lot of these are just theorems that help us know what to look for, where to look. Once we look there, we may have to do some work with like long division or synthetic division, and either it's there or it's not. So we'll go through here. So the rational theorem just says, and again, don't get too caught up in all these different notations. It's just saying, if you have a polynomial, 4x to the 15th plus 2x to the 3rd plus something in between, minus 6, that the number of zeros that this polynomial will have is determined by looking at all the possible well, what we're going to do is we're going to take, this is P, this is Q at the beginning. So what we're going to do is we'll look at 6 over 4, and all the possible multiples of those are where there could be possibly some zeros. Okay, so we take the last term, which is a constant. Remember, it could be a 0, but if it's 0, well, that means that 0 is a choice, right? But not much else. And then we take the leading term, the leading coefficient. And this ratio is going to tell us how many different factors there are. Remember, 1 is a factor of everything. So 4 factors into 1, 2, and 4. 6 factors into 1, 2, 3, and 6. So it'll be the combination of all those. We're going to look at some specific examples, but that's all this first one's saying is for every polynomial to figure out, this is one way to find a possible zero. Just look at the first term, what is that coefficient, and the last term, the constant, what is that, and then it'll give us a way to look at it. Well, pretty close to what I had. So list all the possible zeros for this one. Again, this is our P, and this is our Q. And we're going to do P over Q. And actually plus or minus, they could be either positive or negative. So we're going to look at negative 3 over positive 4, and then all the possible combinations of the various factors of these two numbers. So what are the factors of 3? Plus or minus 1, plus or minus 3. That's it. The integer factors. What are the factors of 4? Plus or minus 1, plus or minus 2, plus or minus 4. So we can do combinations. So possibilities are plus or minus 1 over plus or minus 1. Plus or minus 1 over plus or minus 2. Plus or minus 1 over plus or minus 4. Plus or minus 3 over plus or minus 1. Plus or minus 3 over plus or minus 2, but that's not an integer, is it? And plus or minus 3 over plus or minus 4. But they could be, still all of these could be. So again, we list them all out. So using the different things, it could be either positive 1 or negative 1. Or positive 1. It could be positive 1/2 or negative 1/2. Could be positive plus or minus 1/4. Could be plus or minus 3. And these are fractions. Again, using the rational theorem, let's go back. So those are all the potential factors, right, that we came up with. Okay, so I was just wondering what they want us to do. So they didn't actually want us to find them, but those are, again, part of it is list all the possibilities. And I noticed in the homework there's a couple of these. Some of those could be zeros and some of them probably are not, but these are all the possibilities. So you'd want to be able to list them. So now we're going to use this. We want to find all the zeros, and when we actually go through this, they're going to give us easier ones to work with instead of having to try to figure out if 3/4 is a zero or not. Find the zeros. So we've got 1 and we've got 2, right? So that's 2. Factors of 2 are 1 and 2. So we got plus or minus 1 and plus or minus 2. And the factors of 1 are just 1, so plus or minus 1. So that gives us 1 over 1 or 2 over 1. And they could be positive or negative, so we can check negative 1 or positive 1. We can check negative 2 or positive 2. So if we know those are possible zeros, thinking back to what we just did, what would we do to figure out whether one of those is a zero or not? Synthetic division would be good. Which one would you like to try? Anyone have a, let's go over here. Someone yell out a number. Negative 1, positive 1, negative 2, positive 2. 1? Okay, that's the first one I heard, so let's go with 1. So we'll do synthetic division with 1. Now remember, this is saying, or it's not saying it is, but it's saying it's possible that f of 1 equals 0. Now remember, that would solve out to a factor of x minus 1, so we're going to use negative, wait, 1 equals x, subtract 1, that's saying, yeah, x minus 1. So when we use synthetic division, and remember we always use the opposite sign, so we're going to use positive 1. This is where I said you've got to kind of think through, and for me it's a little struggle to, do I use positive 1 or negative 1? Well, in this case, if I'm going to test out positive 1, I use positive 1, put in the coefficients, so it's 1 plus 1 minus 5 minus 2, and I'll try to get the multiplication right this time. Bring down the 1. Positive 1 times positive 1 is positive 1. Okay, 1 times 1 is 1. And then I add these and I get positive 2. 1 times 2 is 2. Add these, I get negative 3. 1 times negative 3 is negative 3. And I add these and I don't get 0. I get negative 5. It doesn't matter. I didn't get 0. That's not a 0, is it? So we tried it. That didn't work. So I can come back here and say, nope, that didn't work. What other one should I try? Negative 1? Very good. Give it a try. So let's go with green this time. So now I'm going to use negative 1. And again, same coefficient. So you see, it can be a little time consuming, and because you don't always get the right answer the first, So let's bring this down. I get 1. Negative 1 times 1 is negative 1. 1, and I add these, I get 0. Oh, this is cool. Watch what happens. Negative 1 times 0, 0. Oh. I'm doing this, and negative 1 times negative 5 is positive 5. That's not 0 either, is it? It's 3. But it's, so that didn't work. Shoot, I was hoping we'd get one. What's next? 2. Okay, so let's try 2. 1, 1. So you get a lot of practice with this. And part of this is if you're good at guessing, you might guess the right one first and save yourself some. But so we bring down the 1. 1 times 2, this is 2. Add these together, we get 3. 2 times 3 is 6. Subtract, we get 1. Oh my goodness, 2 times 1 is 2. We finally got it. So we tried positive 2. We know that that is a 0. So we know that, yeah, so x equals 2 works. Or if we look at it as a factor, it would be x minus 2, right, as a factor. So that worked. Do we know whether negative 2 works or not? We don't, but probably we're thinking it's probably not going to work. I think it doesn't. If they're going to do it for us, so we'll go through. But we found that one. It's probably not likely that the negative 2, because then we'd have a negative here, and I don't think it's going to work. But I could be wrong. So the thing is, figure out what are the possible rational zeros, and then use synthetic division. And they do the same thing. They tried negative 2. Negative 2 did not work, so it's a good thing we didn't try it again. Negative 1 did not work. So those didn't work. They test the other ones, and they found that 2 worked. And so they know that it factors into this. And then remember, the other part comes from here. There's 1x squared plus 3x plus 1. So those come directly from there if we need to factor it. Okay, so we know 2 works, and then what could we do with this? try to factor it, it's not going to factor. How could we, because that could have some zeros, right? How would we find those zeros? Quadratic formula. So, and we'll do that. So this takes us back to last week, and the way they do it, plug it into the formula. I don't want, again, we've gone through this, so it's going to give you some more practice. So you start seeing in this course stuff we did last week, we use it again this week. So those same techniques. The thing we're going to see, so notice these are not imaginary, these are still real answers. They just have a square root of 5 in it. But what we did is we found 1 0, which was 2, by using this technique, and that allowed us to get it down to quadratic, and the quadratic formula allows us to find the rest, even if they're imaginary. Okay, and we're going to see there's a theorem. If there are any imaginary answers, they always come in pairs. They're conjugate pairs. So if you find one, then you know that the conjugate is also going to be a 0 too, which is kind of cool. So that's how we'd write it in set. Any questions on that, or is that pretty clear? So we're going to use the rational, what do they call it? The rational zero theorem is take the first number and the last number, put the constant divided by the leading coefficient, take all the possible factors of those numbers, and those are possible zeros. Now, it doesn't mean any of them are going to be zeros, but it means that that's one way of getting some possible zeros. And if we can find one, then we get it oftentimes down to a quadratic, and then quadratics we can solve. This is what I was telling you about. It's a property that if there is a root, if one of the zeros is imaginary, they always come in pairs. So if you know that a plus bi then you also know that a minus bi is a root, which is kind of cool, because once we find it, we know, okay, it's just got to happen. Because of the quadratic formula, the plus or minus. That's really where it comes from. So you probably won't, the way you're going to get those imaginary roots is using the quadratic formula. You know that there's that plus or minus, so you kind of see, yeah, it's just got to happen that way. Makes sense. Oh. Anyone else getting tired? These wear me out. So, but you got like 16 homework problems, and so this is what we're doing is going to get you through 32 problems. Some of them aren't too bad, but so to solve this thing, what do we have to do first?
P by Q.
Yeah, find someone give us a possible zero. Let's see. Well, I cheated a little bit. So we know to take the last number and the first number, and again, this first number is 1, and that it's going to be combinations of plus or minus. Now 13, what are the factors of 13? 1 and 13. So we write those. What are the factors of 1? That's where I like, there's only 1 and 1. So it's plus or minus 1. So all the numbers that we have to look at, or it's not too much, is either 1 plus or minus 1. So maybe I should list them separately. It's going to be 4 numbers to check. So either plus 1 or negative 1, and then either plus 13 or negative 13. So those are the 4 we're going to need to use. Okay, we're going to do our synthetic division, and this is where it's probably better than doing long division. Which one you want to try first? Oh, negative 13. You're going to make it hard on me. Okay. Maybe it's the one that works though, right? You might make it easy. We don't know. So, is it Taylor Swift? That's her favorite number? Actually, that was my favorite number. I always like to be odd. Nobody liked number 13, so I loved it. It was my lucky number. And it might work. Wow. It's a long one. So, again, I'll do the first part. You guys do the rest. So, 1. 1 comes down. Negative 13 times 1. Negative 13. Add these together so they're both negative. We're going to get more negative, right? Negative 19. Ooh, We're getting big here. Bust out a calculator. 13 times 19. Anyone got that one for me?
247.
What? 247? That's huge. And it's positive though, right?
Yes, positive.
And then so we add these, so we're now at
269.
269. Geez. And then we're multiplied by negative 13. It's going to be I think it's not going to work, but let's keep going. Because maybe it does. Negative 3,000, blah, blah, blah. It's going to be 3,000 something. It's going to be, so it's not going to be 13. So that's the cool part about this is we don't always we could see it's not going to get where we get a 0, right? So sorry, negative 13, you're not going to work. It also tells me that maybe positive 13 might not work, although it could, sometimes that sign, but shall we try 1 or negative 1?
Positive 1.
Positive 1, okay. Negative 1 here, positive 1. One of them hopefully will work. We'll try positive 1. 1, negative 6, plus 22, negative 30, plus 13. So bring this one down. So there's 1. 1 times 1 is still 1. That's negative 5. 1 times negative 5 is negative 5. 22 minus 5 is 17. Is that right? 17 times 1 is still 17. This is going to get negative 13. Oh, I like it. Somebody was thinking ahead. And then we get negative 13, and then we get our 0. And again, probably negative 1 won't work because the signs will be opposite, but we found at least 1 0, which is sort of all we needed. And so what do we know? 1 is a 0. So x minus 1 is a factor. And then what's the other factor? That comes from these guys here. Remember, 1 less. So this is going to be x to the third minus 5x squared plus 17x minus 13. So that's our two factors now. Are we done? No. Now what we have is we have an x to the third, which we don't have a standard way to do that. We do this all the same thing again with this part. Okay, so what are the possible zeros for x to the third minus 5x squared plus 17x minus 13? Same 4 things, right? Plus or minus 1, plus or minus 13 divided by plus or... So what we would do is we would do the same check again, but this time we would use this smaller one. And if we found one of those, which I'm going to walk us through, actually I looked ahead, x minus 1 is also is a double factor. So positive 1 will work on that one, but I'm going to save us. So this is just, they went through, they checked them all. Notice they checked negative 1 and they checked 1. 1 worked. So they said, okay, we found one that worked. They didn't even try 13. So you guys were brave to at least suggest it, right? And so this is what they got. So this is where we're starting. What they're going to do, okay, so you can go through this. Now we're going to do the same thing with the reduced thing, as we're going to find the zeros there. And again, they do the same thing. Let's see, what time is it? Yeah, we're getting, so I'm just, again, they tried 1 and 1 worked. So what they found is since 1 worked twice, right, we've got 2 factors of x minus 1. And if you remember our multiplicity, what kind of a multiplicity does that give it? It's a multiplicity of 2. On the graph at negative 1, what kind of a 0 are we going to see? It's going to do the kiss the x-axis, as I say, or touch it and bounce off, or from the top or the bottom. I'm not sure which. But so I just want to tie all these things back together. And then notice this was an x to the third, so now it's an x squared. So we have this part. What can we do with that part? Are we done? No. We could try to factor, but that's not going to work. So we use the quadratic formula. And again, I'm going to save myself a little bit of work. We'll let them do all this. Plug it in the quadratic formula, and notice you get a negative inside the square root. So what does that mean? We get an imaginary, a complex answer. And since we get a complex, remember they come in conjugate pairs because of that plus or minus. So our answers, I guess we don't have to put 1 twice, but they did. So the zeros are 1, 1, and 2 plus or minus 3i. Yes?
On the test, we don't have to show all this work as long as people do it. Like if we have a way to do it.
Right. Right.
So for like the complex numbers, you said we could put in the calculator. Can you still have the worksheet?
You can use the calculator. Yeah, you can use the calculator. I would use the calculator, sure. Yeah, because if you're going to come up with 2 plus or minus 3i, that's you would have at least enough. I mean, to do that, to be able to do this, you've got to do at least a little bit of synthetic division to get there. Could just do a guess. Yes. Sure. Oh yeah, yeah. And again, the majority of the test is multiple choice. I can't remember exactly how many, but it was more than 10. It was north of 10. So more than 50% of it is multiple choice. You give me the right answer, I'm not going to ask any questions. Okay. Give me the wrong answer, I'm going to look and see if you had some good work so I could give you some partial. That's the way it'll work. Okay. But you give me a right answer on the multiple choice, I'm not going to ask any questions. On the show your work stuff, I'm not going to get into detail. Oh, you didn't put this part or that part. Show what you need to just to convince me you sort of know what you're doing. And again, I'm not going to spend a lot of time looking. If I've got a right answer and I've got some work, I'm going to be happy. Yes?
Is it paper or is it digital?
It's on paper. It's paper. And so that we don't have access to our computers, don't have notes. And again, I'll let you, as soon as I actually see what it is, which should be by the end of this week, hopefully by Thursday, but certainly by Tuesday, I'll give you more info. Okay. Fundamental theorem of algebra. So if there is any polynomial with a degree of n, so, x to some n power, as long as it's greater than 1, it will have at least one complex root. Okay. Complex, remember, it could have that imaginary part. So everything has a root, is basically says so, right? X squareds we found, even if it doesn't cross the x-axis, it could have 2 imaginary roots. And that's what we're going to find out is that value of n tells us exactly how many total roots there are between between real and imaginary. So if it's to the second power, there will be 2 roots. And they might be real roots or they might be imaginary roots. If it's x to the 5, there will be 5 roots. Some may be complex, some may be such. So it's just saying, and then so with that in mind, again, don't get too caught up in what all these things mean. It just means if we have a big, long polynomial, maybe x to the 157th power, we could have a lot of stuff going on. But what it tells us is we can rewrite it as a series of linear functions that we can factor it all the way down, just like using these techniques we've gotten, right? We may eventually have to use the quadratic formula, but we'll be able to find these zeros. At least they exist. Now, C does not have to be, they're complex numbers, so they could be imaginary. It doesn't say that we can always find them all, but it says that they will exist somewhere. So we can get them all down, and then we can find out what this coefficient is. So we're going to take a look at one example here that they give us. Let's see. So find a third degree polynomial. Let me back this one up. Okay. Maybe I had this. Okay. Find a third degree polynomial with real coefficients that has -3 and I as zeros, such that f of 1 equals 8. So they're giving us 1, 0, and they're giving us this 0. So if I is a 0, what else is a 0? Remember, if imaginary, they always come in conjugate pairs. So this is really, think of I as 0 plus I, so that's conjugate would be 0 minus I or just minus I. So these are the 3 zeros. And so to write them as factors, we solve for 0. So I would add 3 to both sides. X plus 3 equals 0. This one I would subtract I. X minus I equals 0. This one I'd add I. X plus I equals 0. And so it does tell us that's what they've got, the 3 factors. But there might be some coefficient out front. Okay, and that's where we're going to use this f of 1 equals 8. And so that's where we get down here, right? The factors, they multiplied it back out. I would probably just stick with this first one. And what I would do is that f of 1, so I plug in a 1 for each of these x's. And I know that that has to equal 8. I'm going to go to the, see what kind of, how we're getting tight on time, so we'll go to the next page. That's what they do is f of 1, plug in 1 for all of them, it equals 8. Do the math, they get that that leading coefficient in this case was just 1, but it might be 2 or something else. So you're going to have some homework problems like that where they'll give you one of the zeros, maybe some of those, you'll be able to factor it, but just recognize that that theorem says that it will factor into linear things, but there may be this coefficient here. And we're going to stop about there. There's one more concept to be able to finish this up. We'll start Thursday with that, and then we'll go into the rational functions, and we'll be all good to go. I'm tired. It wore me out.
Had a lot of calculations.
Yeah, it's but hopefully not too bad. Just tedious, right?